welcome to the last of the morning session. It's basically talking about geometry in reaction network. Okay.
Thank you. Yes, thank you everybody for being here. Thank you for the invitation. And yes, I'm going to talk about the algebraic geometry. That is in reaction networks. And the first thing is, what is a reaction network? So what is a reaction? I'm sure everybody has seen a reaction. So examples of reactions that you might have seen. You have two molecules of hydrogen, and you have one molecule of oxygen. And then they come together, and then you get water. So any chemistry class, you have seen a reaction. Also, if you have fat, so a tray slicer, and you put it together in 3 molecules of caustic soda, then you get soap, soap, and glycerin. So those are reactions. Then what is, you cannot hear? What about this? Maybe I should just speak louder. Okay, that works. So reactions appear in chemistry. But also in biochemistry. Maybe representing processes that take place between proteins in a cell. So in general, I am going to say that a reaction network and I would probably write reaction network is just a set of interactions that take place between certain species. Those species can be molecules, they can be proteins, they can be animals, they can be groups of people, and they can be represented by means of a directed graph. Where each node represents a complex. And a complex is nothing but a linear combination of the species. With integer coefficients. Actually, non-negative integer coefficients. And I don't know if you can see below this, maybe I go to the other side. So these are the nodes. And then Each edge represents an interaction, so a reaction. That takes place between two complexes. We have the Sowers complex. That we will call the reactant. And these reactants, by this interaction, get transformed into the product. So a reaction network is just a graph in this sense. Let me show you some examples. My first example will be just given by two species, A and B, that get, on the one hand, transformed into 2 times B when they come together. And then also, B by itself is somewhat transformed into A. So this is a small example where issues are A and B. Complexes are A, B to B, and A plus B. And then we have 2 reactions. Another example, the bigger one. I have this reaction. When I write the 2 arrows on both sides, it means there are 2 reactions taking place. So this means x1 goes to 2 times x2, but also 2 times x2 goes to 1. So I just repeat it. And then I have this, they call a reversible reaction. It goes both ways. Goes to x4, which goes to x2 plus x5. Sorry, plus x3. Which goes back to x1 plus x3. So here I have 4 species. And I have, so 2, 4, 5, 6 reactions. That take place among 1, 2, 3, 4, 5. One last example that will appear. B goes to A, and then A plus 2, B goes to 3. Again, another small reaction network with 2 species. I have 1, 2, 3, 4, 5. So the nodes are complexes. Some of them appear in several reactions. So they will be the reactant, some reaction, but also the product. It will depend on how I label them, and this can change depending on what's convenient for me. Okay. So as I said, those are examples of reactions, but I could also find, I could also represent like these interactions between animal species if I want to study a problem on population dynamics in ecology, maybe. Foxes and rabbits. Rabbits are born. Fox meets a rabbit, then there's no longer a rabbit. Then eventually there will be 2 foxes and so on. Also, this compartmental models that one can use to somehow divide individuals into groups. So for instance, in epidemiology, this SIR models where you divide population into susceptible, infected, recovered, and then you have susceptible means meets infected, and then you have 2 infected, and the infected gets recovered, and more elaborate versions of this. So it can be used really to represent many types of interactions. So what's the goal of this course? My plan is to use today to let you know what does this have to do with algebraic geometry. So where is the algebraic geometry here? So I'll introduce you a little bit to the framework. Then on the second lecture, I will give you more of the framework and some features, properties, things that one can be interested in. And then the third and the fourth lectures will be about probably specific problems that one can study and some results that have been found there. So this is the plan. And then I'm gonna come back to the formal definition. Well, so I said this is just a graph. And then we will write for a reaction network, G, a set of species, complexes, and reactions, where X will have n species that in general I will write by X, like big capital X. The reactions will be of the form such a linear combination goes to some other linear combination. And I will have R reactions. So I need coefficients for each reaction for each species in the source complex and in the target complex. And then, maybe I put it here. D will be the set of complexes. So it will be the set of linear combinations, either written like this or like this, such that this is the Sowers complex. And when I write the primes, I mean the target complex. So all of those for all the reactions. Maybe I write them like this. Or in other occasions, maybe I'll write just y prime such that there is a reaction having those as source. So now, the idea is to understand how the population of those species evolve in time. And under certain assumptions, namely that the concentrations are relatively high in the environment and that they are uniformly distributed, we will model the evolution of these concentrations by an ODE system. So we will write x1 like small x for the concentration of species big x1. And in time, it will evolve. In a way that is determined by a function that does not depend explicitly on t. So it only depends on the concentrations of all of the species involved at that time. So we will have one such function for each of the concentrations of the species. So we have n functions for n species. And this gives us an autonomous ODE system. And we will, yeah. So I stands for the concentration of the ith species, and this is a function of the times, actually. And we will abbreviate the system. Like this, where x is n variables, and f is n functions. So these functions we call the species rate or the species formation rate functions. And one observation to do here is that as the variables encode concentrations of species, it might only make sense biologically or chemically to consider positive or non-negative concentrations. So those variables will take non-negative values. But actually, if one concentration goes to 0, then this means that that species is extinct. So most times we will focus on positive concentrations. So normally, we will be interested in the positive values. So now when I wrote the complexes here, I said I call Yj this linear combination, but I will actually identify this with a vector of the coefficients of this complex. So it would be a vector n entries which are positive or non-negative. Numbers, meaning how many entities of each species inform that complex. Now, each of them of the species formation rate functions is trying to determine how the concentration of one of the species evolves, and this depends on the kinetics. So we need functions for that tell us how this evolves, and those are linear combination of what I will call the kinetic functions. The kinetic functions give me a function for the kinetics of each reaction. So for each reaction, I have a function from the positive reals or the non-negative reals to reals. And then those functions are just linear combinations of those kinetic functions. And the coefficients come from what we call the stoichiometric coefficients. And those are the stoichiometric coefficients. So those give me the stoichiometric coefficients, the coefficients of the linear combination of all the species in the complex ID. And I say they come from the stoichiometric coefficients. And the thing is, if I give an expression for this fi will be something like this. For each reaction, I have the corresponding kinetic function, and then the corresponding coefficient comes from, well, I'm looking at the evolution of species I, so I need the stoichiometric coefficients for all the reactions for species I. So this is why I have here that index I. And this tells me how much of species I is created minus how much is destroyed in the reaction one. The same for all reactions. So I will go to the examples now.
Yeah, this or
sorry?
Yeah, or is this or equal?
This one?
R.
R is the number of reactions.
You have n considered for coefficients. So R should be this or equal to n.
No, not necessarily. So R is the upper index. It goes with the reaction. Either I'm making a mistake here. So the upper index goes with the reaction. This is why I'm using here from 1 to R. It comes from 1 to R kinetic functions. And then the sub-index come with the species. So here, all of them are I. And here, the sub-index go from 1 to N, while the J's go from 1 to R. Okay.
Sorry, shouldn't,
but with the example,
shouldn't there be a reversible arrow in R? The reversible arrow in R, like it goes only forward, so it can be backward reaction as well.
So some reactions can be reversible, but then I will, with this notation, I will consider them as different. So I would like write this graph with 6 different reactions. Okay, I will do this now for the examples. Just I wanted to say that this kinetic functions need to be continuously differentiable. And yeah, some other assumptions that make sure that they are only positive whenever all the species that are involved in that reaction are present. But we will go to very specific kinetics very soon. So not so much generality will be needed here. And then when I give a choice of kinetic functions, for a given network, I get a kinetic system. So I will add to this species set, complexes set, and reaction set, the set of kinetic functions. And then it is a reaction network together with and the goal of all of this is, okay, we are not going to solve the ODE system. We are not going to find a solution for the ODE system. But given just the structure of the network, given the complexes, given the reactions, what can we say about the dynamics? Or what can we say for a certain class of kinetics? But this may be for class of kinetics. And when I say behavior, I mean how do the concentrations of the species evolve? And I said I'll go to the examples. But first, let me write one efficient thing more. So now, if I have a reaction network and I add a kinetics, I get an ODE system. And by what we've seen here, we can write the system as the product of a certain matrix times a vector of kinetic functions. So we have one entry of the vector for each kinetic functions. And then this matrix will have as entries maybe I write all of this. The first entry, so it will have one row for each reaction, because then it will multiply this vector, and then it will have, one column for each reaction, and then one row for each species. So for the first species, first reaction, it goes like this. Still in the first reaction, the last species, I get this coefficient. So it's the coefficient here minus the coefficient here. It is the net production of the species in that reaction. And then it goes until the last reaction, where I would have first species, last reaction. And now last species, last reaction. So these entries will be integers. And we have one column per reaction, one row species. So going with these examples, maybe so you can see the first network. Now I can compute this matrix gamma. So the first entry needs to talk about the first reaction and how much of the first species I get. So I lose one A. So there would be a -1. And I get one B. So it would be positive. But for the second reaction, it's the opposite. I gain one A. Then I lose this. I'm seeing that actually this wasn't fine. So I had 5. Sorry, that was a mistake. So if I use this network, then I will have 5 times 6 matrix. And it will go something like this. So the first reaction loses 1x1, produces 2x2, and so on. And the matrix. So as it is reversible, every time it is reversible, I will have 2 columns, one for each weight. And it's just the opposite sign. Then the third reaction would be this, and as it is reversible. And now there are 2 left. And hopefully I didn't make any mistake. Now for the last one. I get a matrix that is very similar to the first one. Just signs and change. In this last column, yeah, definitely. Last one. Thank you. So this here is what we call the stoichiometric matrix. All right. It is made up by the stoichiometric coefficients. I said I want to understand the behavior in terms of how the concentrations evolve. But I also said that I'm not going to solve the ODE system. And we are expecting some algebra, so let's get there. So instead of looking at the whole solution of the PDE system, given a kinetic system, so network with the kinetics, I call a steady state. Of the kinetic system, any steady state of the ODE system, so any equilibrium of the ODE system. So it will be a non-coupled one value for each species that gives me a state of the concentrations. Such that it takes all the species formation rate functions right. So it is a common solution, real solution of the equations f1 to n equals 0. As we are interested in the positive solutions, sorry, in the positive concentrations, then we will be interested in the positive steady states. And I will say that a reaction network is consistent with some kind of kinetics if it allows some positive set states. So there are actually some solutions to these equations. Now I said we want some algebra and some algebraic geometry. And this comes when I consider a certain kind of kinetics that is called mass action. The names. So I will assume that this law holds, and it requires that the species are homogeneously distributed in space and they are relatively high concentrations, as I said. And then it says that the speed at which a reaction takes place is proportional to the concentrations of the species that are involved in that reaction. So under this assumption, my kinetic functions would be of this form. So for reaction J, I will have a function that is proportional. So there would be some constant here to the concentrations of all the species that are in the reactant of that. I will have the stoichiometric coefficients the lowest exponents of the monomial. And I will write this also abbreviated like this. So it would be a monomial with multi-exponent given by the Stowers complex of reaction A. And then this constant here would be also positive. And this is what I call the reaction rate constant. And we sometimes label the graphs with them. So I will write here two reaction rates. Made a mistake. This way I'm also given numbers to the reactions. So for the examples, I will have under mass action, I will have the system given by the matrix I just raised times a vector of monomials that needs to have two monomials. The first one comes from the first reaction. So let me encode concentrations like this, XA and XB, or A and B. And then the second one will be this. And this is how it goes. So now here my functions would be, if I remember, this matrix was -1, 1, 1, -1. So F1 is this. And F2 is something like this. And now I have polynomials whose monomials depend strongly on the structure of the network because they come from the complexes. So the support of all the functions is given already by the Stowers complexes. And they come together with, well, they have coefficients given by the stoichiometry, but also they have parameters in the coefficients. And not any parameters. Every parameter always comes with the same monomial because it goes attached to one reaction. So my functions are polynomials that are linear combinations of terms, where each term is of this form. It is a certain monomial together with its own terms.
Excuse me?
Yep.
The law of mass action which we used to study in chemistry was that the rate at which a reaction takes place is proportional to the concentration of reactants only. The species can be different in reactants and products, and you have mentioned that the rate of the speed at which a reaction takes place is proportional to the concentration of species.
In the reactant.
Competition in reactants and products.
In the reactant. Only in the reactant.
Only here.
Yeah, this is why the coefficients that I'm using here four exponents are only the ones that are the source of this. Yes, maybe I didn't say the word. I'm sorry. Yeah. So it takes of the species involved, I mean, yes, so that the reaction takes place. Yeah, thank you for that. So let's see how much time. Now, if we just to make a connection to Thomas notation, because I will also use it. If we write B, a matrix that collects all those coefficients in the reactants. So I will have a matrix that has one column per reaction again, and one row per species. But now I only take into account the alphas, the coefficients in the reactants. Then this is a matrix with non-negative integers, which is n times r. And I will write this for a vector of monomials. So this will be the vector which has the column 1 of this thing, and then the column r. And using this, I can up here. Then I get a system that I can abbreviate as the product of the stoichiometric matrix times this vector of reaction rates, and then times this vector of monomials. And this will give me my ODE system. Or maybe I write sometimes like this, where I'm putting here a diagonal matrix with the case in the diagonal. This is the Hadamard product. So product entry by entry.
We have a question. So the example you were giving us, I think now they're both covered. But so
the one above.
Yeah. So this is the one corresponding to the one you wrote that's covered also. So, but is the two, do we see the two somewhere? Should it be like a xb squared or something like that in the first?
No, because I'm only considering here, so as she pointed out, I'm only considering the species in the reactions. So for having some power of one of the variables, I will need to have some coefficients in one of these species. So it will happen here. Okay. Here, my vector would be so yes, I can have higher powers in the matrix.
Okay, thank you.
Thank you for the question. So any reaction network with mass action kinetics gives me a system of ODEs like this. And then if I want to study steady state, then the steady states are the positive, sorry, the real solutions. I'm only considering all steady states. To the polynomial system. And here is my algebra. And now, under this assumption, of course, I can, under this assumption, I can consider an ideal generated by the functions f1 to fn, which now are polynomials. Real, say, in the variables x1 to xn. And I can consider a variety defined by this ideal. The complex or the real, whatever I want. But as I want to consider only positive steady state, then what I have is not really a variety, not an algebraic variety, but a semi-algebraic set. And I call I still call it a variety, but I say the positive steady state variety. And I really mean the intersection of this algebraic variety with the positive order. So this will be a semi-algebraic set defined by equalities, these equations, and then inequalities telling me that all variables need to be equal. And just to see the examples, even if I just erase the other one. So in the first example, I had equations as 1 equals this, and the second one was minus this one. So if I want to look at the algebraic variety, I can forget about this one because it is just redundant. And I can consider, I will write something like density V for the steady state variety. Then maybe make it depend on the K. So if I want to consider the positive steady state variety for this network, maybe say I take K to be 1 and 1. So this is 1 and this is 1. So for 1 and 1, this would be the set of all x, a, and b where, well, either x, b, x, 0, but I don't care about the solutions that are 0. So I can factor this out. And then I have minus xa plus 1. So these are all the pairs one xb, where xb is constant. This will be my steady state variety. So you can do the computations for the other examples in the test. And now that I have all these definitions, the goal of all of this is to try to determine properties, mathematically, the goal would be determine properties of the positive steady state varieties, which are determined by the network structure and the kinetics, assuming mass action kinetics. But actually, the values of the parameters, of the reaction rates are normally unknown, or they depend on the environmental conditions, and they are measured in the laboratory, so they would be numerical approximations. So I want to determine properties that are not very sensitive to these approximations. So I want to consider the whole family of positive steady state varieties parameterized by K. So I will consider the K's here as parameters that can take positive values. And then what I have for a reaction network with mass action kinetics is a system of polynomial equations with a very specific structure with parametric coefficients. And I want to look at the positive real zeros of that.
I have a question. Can I ask a question?
Yeah, sure.
Yeah.
Okay, so is there any condition on PIs such that VI is not equal to 0? Since we are working over R, so that's why the Hilbert-Nussbaum theorem doesn't hold. So is there any guarantee that VI is not empty?
No, of course not. No. So to begin with, we are looking at the reals, which can already make it empty. So the polynomials have real coefficients, but this does not mean that there are real points there. And of course, it does not mean there are positive points. So I made a definition before saying a reaction network is consistent if it admits a positive steady state for some case. So only consistent networks will have solutions for some case. There are some networks that are not consistent with mass action. That's a very good question. Thank you.
Thank you.
Yeah, so just to finish, of course, the idea of all of this for the biology and the chemistry is to guide experiments. So if I can understand the equilibria that are expected from a model, even if I don't know the exact parameters, because when I do the computation, if the computation depends on the parameters, then it may not match what I'm seeing in the experiments. But if I know what should happen, like for general parameters or up to some variability of the parameters, then I can say much more. And then I can decide whether a model fits what I'm seeing. So the idea is to guide experiments, to make model selection for systems biology. That Iram said yesterday was one of the ideas of this book. Or maybe try to design networks that have a certain behavior for synthetic biology. So yeah, I think this is all I have for today. Thank you.
Is there any question?
After translating everything into the language of complexes, so what is the underlying question we are going to address?
There are several questions that we might address. So for instance, yeah, as the question that I got from Karachi, are there any positive steady states at all for this network? How many are there? Are there infinitely many? Are there finitely many? And moreover, if I start with an ODE system, and we will see this in the next lecture, I start with an initial condition. This initial condition will be giving me maybe some conserved quantities. So for instance, here I said F1 is minus F2. So this means F1 plus F2 is 0. F1 is the variation of X1, and F2 is the variation of X2. So this means that X1 plus X2 is constant, always. So maybe I want to ask within a certain, so for an initial condition, can I reach more than one steady state, or can I always reach a steady state, or for which initial conditions I can reach a steady state? So I will talk about some of these questions in the third and fourth lecture, and some other geometric insights.
And are they going to address certain questions from the model side when people are studying in SIR models?
I'm not. I have not worked with SIR models, so I don't know if the questions that arise are the same. The networks that I see are mostly coming from biochemistry. So apart from the theoretical side, what I've seen is people working with bacteria, antibiotic resistance, some mechanisms of this type. So I don't know if they behave the same. Apparently, in chemistry, some things happen that in biochemistry are not so likely to happen. So biochemistry is very special in the way networks confer certain properties, but I don't know why.
Need reference of this thing?
Yeah, I can give you later, or maybe we can post it. Yep.
All right, maybe this is a little of an annoying question, but so the mass action law is quite old, I guess, and is it still? I mean, it conveniently gives us these monomials, but is it actually something that is still in use in like a chemistry community?
So I've asked this to some of my colleagues, the ones that are on the biological side. It depends on the kind of systems that you're using. But actually some of the dynamics some of the kinetics that they consider can be somehow translated into things that also become polynomials. And yeah, you can do something to translate that. I guess not for all cases, but I think it still makes sense. I believe it still makes sense to study this. Though I am actually using it for real life.
Okay, is there any other question from IBA? Or from online participants? Okay, if there is no question, so let's thank the speaker. Okay, now we have a lunch break and we will meet again at 2:30, right? So our evening session will start at